compass anywhere on surface of Earth, the needle will show the direction towards the magnet pole. But because this is north magnetic pole of the needle, it is attracted by actually the south magnetic pole. But the naming convention is quite tricky. So if you see this image to the right, you have north magnetic pole, north geomagnetic pole, and geographical north pole. So you have everywhere north poles. So when we say about this magnetic poles, we are using north pole because we are stressing that it's located in the northern hemisphere. It's close to geographical north pole. But in reality, if we put some bar magnet inside the Earth to produce this field that we can observe on Earth's surface, it would have south pole near the geographical north pole. By the way, if you're using compass, it's pointing towards the magnetic pole, and this angle between geographical north pole and magnetic pole, so it is called declination. So if you're using your compass and you want to know the direction towards the true north, so the geographical north, you need to know the declination, so this angle between, and add or subtract it from the direction that is showed by your compass to correct it for this declination. Now, what is this north geomagnetic pole? Because you have magnetic pole, geomagnetic. As we mentioned before, at the magnetic poles, the magnetic field lines are vertical, right? Another angle that is used to describe magnetic fields is inclination, and inclination is this vertical angle. So in this example, generally inclination has 90 degrees at the pole, which means it is vertical, and it would have 0 degrees at the equator. This north magnetic pole shows where these magnetic field lines are vertical. So what is this north geomagnetic pole? As I said, if we are trying to describe these magnetic field lines produced by Earth, then we can pretend we have a bar magnet inside our planet. And we can calculate at what position this bar magnet should be placed to mimic these magnetic field lines. This is just a simulation, but it shows this magnetic field produced by the Earth. And if we draw such bar magnet, then we would by calculations we can see that it's tilted with respect to the rotational axis. Its magnetic pole will be located here. So they differ. So it differs from the real north magnetic pole. Okay. Now let's go back to the quiz. This question is in connection to my previous lesson about auroras, but I think it's easy enough, so even if you didn't participate, then you can still answer this, I hope. Yes, so far away from the Earth's surface, the geomagnetic field lines are controlled by solar wind interaction. Solar wind controls the shape of the Earth's magnetic field. But what is happening closer to the Earth's surface? What do you think? I already mentioned it, but Yes, as I said, good approximation of the Earth's magnetic field is the one produced by a bar magnet. So let's go back to the presentation. So you can see that the field produced by a bar magnet is really similar to the field produced by Earth. Okay, but we are talking that we have this magnetic field produced by Earth, but what's the source of it, and where is it created? So here you can see our planet, and it consists of few layers. The outermost layer is crust. So this is what we see land and what we see the ocean. Then we have mantle inside, and the innermost part of our planet is called a core. And core divides into inner core and outer core. Inner core is solid, while outer core is liquid and it's iron-rich, and movements in this outer core create this magnetic field. So we cannot say that magnetic field extends from the Earth's surface, because it starts already in the core. Well, generally, magnetic field is created in there, but you cannot distinguish really the source of it, like the beginning of it. So you have these lines that are extending out of our planet, but they are also inside the planet. But as you can see here on this simulation, they are really tangled inside. So this is where the magnetic field is created, the main magnetic field. But if you have observations made by magnetometers on this Earth's surface, and if you sub this influence from the Earth's core, you will still be with some magnetic fields that we don't know what's the source. So now we will answer this. What's the source of this anomaly? Because we call the difference between our magnetic measurements and the Earth's magnetic field originating in the Earth's core, we call it magnetic anomaly. So we all know about anomalies caused by space weather, but it's time dependent. And we measure this magnetic field during quiet times, we still will get some magnetic anomalies. So now, what is other source of magnetic signal that we can observe on the Earth's surface? And to talk about it, we will first talk about seafloor spreading process. You probably heard about tectonics, which this whole theory describes the motion of plates, lithospheric plates. We have three types of plate boundary. We have divergent plate boundary, where these lithospheric plates are moving away from each other. We have convergent plate boundary, when one is when they are moving towards each other, so they are colliding with each other. And we have transform boundary, where these plates are just sliding against each other. But what does this plate tectonics have to do with Earth's magnetism? So if we look at seafloor spreading center in the oceans, it's divergent plate boundary, so these plates are moving away from each other. And then the new material is rising here from the mantle up, and as it cools down, it contains minerals that record the Earth's magnetic field. And as they cool down, they get this permanent magnetization. So if we make magnetic measurements of the ocean floor, we will see what was the magnetic field at the time when this new crust was created. And again, I showed you this picture from natural occurring rock, which contains which creates magnetic magnetic field around it. Okay. Yeah, now the quiz again. Okay, so the image shows the boundary between plates that move away. What can you see? So you have this plate boundary that is here in the middle of this magnetic image. Is it total chaos, or do you see parallel stripes? This is, by the way, plate boundary near Iceland. Okay. Yes, of course, you could see stripes parallel to the boundary line. And why these stripes are occurring? So let's go back to the presentation. As I said, when plates are moving away from each other, pneumatic is rising, and it records the magnetic field, Earth's magnetic field that is that's at the time of this was being created. And here is another image that you can see that there are the stripes where you have, for example, if you measure intensity of magnetic fields, sometimes it will have positive value and sometimes it will have negative value. And as these plates are moving away from each other, these stripes are created because this older crust is then going away from the plate boundary. But what these stripes really mean? Because this polarity is different, it means that there have been poles reversals in the past. So in the past, Earth's magnetic field was changing the location of magnetic poles. So what is now the magnetic pole located in the northern hemisphere, of south polarity, it used to be north polarity. So you have stripes of different polarity recorded in the Earth's crust. Let's go back. Quiz. So alternating stripes indicate that the boundary was rotating or the magnetic poles have reversed their position in the past. Yes, as I mentioned, magnetic poles have reversed their position. So generally we get information on previous state of magnetic field based on magnetic measurements of the crust at the bottom of the oceans. But what about land? What about the land? Here is an example. Because we will also talk a bit about Svalbard, because Polish Polar Station is located in this archipelago of Svalbard, and here you can see Greenland. This is a normal map because this one is a bit rotated. So you have you can see here Atlantic Ocean, and the plate boundary here is of divergent type. So these plates are moving away from each other, the North American plate and Eurasian plate. And the crust is being put at the plate boundary here. What does it mean? It means that we can trace, based on these magnetic measurements, we can trace the movement of Svalbard towards the time when it was located very close to Greenland. This happened around 60 million years ago, when this part of Atlantic Ocean started to open. And this is magnetic image of this plate boundary. You have Greenland in the lower left, but you cannot really see Svalbard here. It's just this red color here indicates the Yermak Plateau, this plateau located here. But we have magnetic measurements here of the plate boundary, and you can see this alternating stripe indicating alternating poles, pole reversals. So we can, if we date this rocks here, we can see how long time ago was Svalbard near Greenland. And generally in the whole world we can trace such signals. And yes, but this is just showing us the results up to, let's say, like in this case, around 60 million years ago. But what about earlier history? So the same thing as is happening at the boundary on the between divergent plate can happen on land, because if we have volcanism, then we have also this material coming from inside of the earth, from the mantle, which is erupting, and it's molten, and as it cools down, it also records information on the Earth's magnetic field. So if we take rock samples from that, we also can say something about paleomagnetism. And this is more convenient because basically on the ocean floor, the oldest rocks are around 200 million years. And we would not get information prior to this time. But if we take samples from land, we can trace magnetic fields back to 3 billion years ago. And such investigation, magnetic investigation here in Svalbard, showed the long trip of this archipelago. And this is well, latitudes, and right now Svalbard is located in the Arctic. But if we trace it back in time, you will see that it was closer to the equator around 400 million years ago. Before this, it was located in the southern hemisphere, and this long journey is reflected in geology. So if you geology of Svalbard, this map here is a simplified geological map. You will see the oldest rocks are located in the western margin. They are much older than 500 million years. So these are the oldest rocks, and they were created. Well, there were a few times where Svalbard was colliding with Greenland, so there was a lot of activity creating mountains, and I will show you pictures from Svalbard so you can see how this looks like. But generally, it was a long time ago. The younger rocks are placed in the center of the main island of archipelago, because this island here is called Spitsbergen. By the way, Spitsbergen, the whole name comes from these mountain peaks that are very steep, and they remind of Alps. If you see it, just they are not as tall. Yeah, but generally, if you compare this layers of rocks that can be found on Spitsbergen and Svalbard, you will see that after these oldest rocks, which are called Hekla Hoke, by the way, you have time when Svalbard was located near the equator. It was in Devonian time, and rocks from this period are of red color, and they indicate there's desert-like conditions. Later on, as Svalbard was moving towards the north, this climate of Svalbard was switching towards more tropical climate, and you can find fossils of trees preserved in rocks. You can see carbon. You can see coal in the rocks, and you may probably, I don't know if you have heard about it, but in Svalbard there is a mining industry, coal mining. So we are extracting this coal from the rocks. So generally, we can this really long way back in time of Svalbard. So if anyone ever asks you about if Svalbard could be tropical island back in archipelago back in time, you can say yes. At some point it was located in the tropical zone. Okay. So to end the quiz, I will show the last question, and then I will show you some pictures from Svalbard to show you this long history preserved in the rocks. Oh, two more questions, yes. So the first question is, the boundary where plates are moving away from each other is called convergent plate boundary, divergent plate boundary, or is it a transform boundary? Yes, so most of you now answered correctly this question. And the last question is again the image that I showed you at the beginning. So this upper part of the plate boundary showing this parallel magnetic stripes, what kind of plate boundary is this? Is it divergent, so the plates are moving away from each other? Is it convergent, so they are moving towards each other? Or are they transform boundary? Or you have no idea still? Yes. Okay, so generally now you were able to answer this question. Okay, so now we have a few more minutes to see these images. So I told you that we can trace continental motion back in time, and there are many. Please play. Okay, my internet is not good enough to play it, but generally you can find on the internet this animation. It's one of the models that can be created of how this plates were drifting in the past. So I will just show you quickly like this. That if you show it, if you see it normally, you'll be able to see the whole motion. Yeah. Okay. Sorry that I cannot show you videos today. Okay, but pictures. So pictures. So this is the view for Hornsund Fjord. The Polish polar station is, you cannot see it. It's located more towards the right side of the image. And this is the closest glacier from the Polish polar station, Hans Glacier. And generally you can see this landscape that is characterized with these mountains. And this is western margin, so these mountains, they were created during many collisions with Greenland. And because of these collisions, all the rocks here, they are really folded, and you can see layers of rocks that are not horizontal, they are folded. It means that the conditions here, they were really compressing these rocks. You can see that layers that normally should be horizontal, they are, well, it's around 30 degrees, striking 30 degrees, dipping. This is picture from Longyearbyen, and here it's a bit different landscape, and you can see these parts that are of rocks that are from just going out of the snow. They are rocks containing coal. So you cannot see it on this picture, but there is a coal mine in Longyearbyen. It mines coal from these rocks. This is back in Hornsund. So these mountains, they are really old mountains, older than half billion years old, and this is why Spitsbergen is called Spitsbergen, because of those peaks. Yes, here another just indication of really complicated plate tectonics. You have here, for example, this layer of rocks that is thicker in one part, and it thins towards the other part. And this red color is from iron-rich rocks that are oxidized, so you get some kind of a rust color. This is in other direction than the Hans Glacier from Polish Polar Station, so it's the view towards west from the Polish Polar Station. You can see this more like Alps mountains. Yeah, and this is already the landscape in the eastern part of Spitsbergen. We went on a trip to the east coast, and here the landscape is generally not as steep. You can see these mountains are more like a table mountains, and still you can see these different layers of rocks now are almost horizontal. And this is a piece of rock that I found last year. This is some leftover, some fossil probably from a reef, indicating marine environment at the time of this rock was created. Okay, so I hope you have now some better understanding of magnetism, how this enables us to say something about Earth's history. I really recommend you just Google on YouTube some videos of how these plates were moving in the past to see this really nice journey of plates. If you have any questions, you can ask.